Welcome to Construct Canada. This feels like the unofficial kickoff of the Christmas season in the construction industry. I'm very glad to be back. Both myself and my colleague Dave have spoken here before, and it's always a great venue. So thank you all for coming out for the very first session in the morning. It's nice to see a few bums in the seats. It's quite often more in the afternoon, so very welcome for you all to be here. The flavor of today's presentation is going to be I'm sort of covering the past and present and some of the materials that you may see in the future, a little bit of the basics of curtain walls, and Dave is going to take that and talk about future challenges. So codes becoming more challenging, energy efficiency requirements are ramping up, and where and why we might see some of those new materials, some of those innovative products that are coming in the marketplace now, where they might really be needed to meet those demands, what the future might look like, how things haven't changed an awful lot in 25, 30 years in a sense in terms of materials and usages, and how that's going to change quite a lot in the next 5 to 10 years. Ontario Building Code 2017 is one of those magic numbers where energy efficiency requirements really ramp up, and meeting those demands is going to be quite challenging. So that's a little bit of, I'll look at sort of past, present, Dave's looking at the future, and we'll go from there. So a little bit about myself. Been with Morrison Hershfield 19 years now. So I'm responsible for the building science practice in Eastern Canada. So we have offices in 4 locations. And I get to manage talented guys like Dave and others. So he has really the day-to-day knowledge of some of these new projects. We've got some great stuff on the go. And so Dave really is our practice lead for facade engineering in the GTA and a broader perspective, sort of the Great Lakes region in a sense. So a little bit of that sort of past and present. So what do we expect from a building envelope? Well, money's always part of it, right? That's a very large one. So it's got to be cost effective. Durability is always a challenge. If the water management details don't work well, and if the condensation resistance and all those kinds of things don't work well, you get premature failures and premature deterioration. So sort of hand in hand with that, if it's durable, it's probably going to be low maintenance. But of course, the primary one is, does the system work as an environmental separator? So temperature, heat, air, moisture, both from precipitation and vapor flow and all of those things. And in recent years now, it has to be green, or at least seen to be green. And what does that mean when we're talking about some materials that have very big carbon footprints, like aluminum? It takes a lot of energy to get it out of the ground and to smelt it and to manufacture it. And so, is that going to be a big driver in the future? Is aluminum, for example, going to be less commonly used? Other materials take its place. Some of that could be a big driver of, say that. Some parts of the world, there are actually carbon trading, so the industry has to pay for the carbon footprint of some of its materials. If that comes into play in North America, aluminum will be at a big disadvantage compared to wood and some other materials. So that's very much crystal ball. Who knows whether that might happen, but those are the kind of things that may be coming at us. And for all the architects and owners in the building, it's got to be beautiful, right? Can't just be like everything else. So the challenge, the energy efficiency requirements, that's going to be a huge driver in the next 4 or 5 years, getting to jump that next hurdle of the 2017 energy efficiency requirements. And since windows and curtain walls have such a low R value, they are kind of that low-hanging fruit. If you can improve the R value, the energy efficiency of those portions, you can have a huge impact on the overall. Changing your opaque walls from an R15 to an R20 doesn't actually have as much impact as changing that from R3 to R4. So that's kind of what we're talking about. Or the trade-off might be, if you can't improve that, then you have to have less and less glazing. So buildings will start looking a lot different than they do now. Glazing ratios will have to drop. There'll be less vision area, more opaque areas. So buildings might look quite different in a few years to meet those energy requirements. So that's going to be the big challenge, is how do we balance the aesthetics, the energy, and the performance. So this is one that Dave loves. It's that expectations of, I want everything, I want it in one bag, but I don't want it to be heavy, right? we want it all. We don't want to make it difficult for us. So the outline, I'm going to cover the first 2 or 3 of these, just some of the basics. We'll sort of talk about, that's a little bit of the past and present, where we'll see that some extrusions and some profiles haven't really changed since the late 70s, early 80s, and sometimes for good reason. But how we use those differently in the future is going to be an interesting conversation. And then curtain wall innovations. So what sort of materials are coming into play? Some have already entered the industry in a small scale and may do so on a much larger scale. And then Dave's going to talk about building energy regulation. So why would these innovations now maybe become more commonplace? It's all going to be driven by codes and performance requirements. And then a good case study at the end of how to use this, and profiling a little tool that we've developed internally to help navigate through that mess of data. So where some of this is driving us is much more detailed component modeling, full building energy modeling, and now you've got the challenge of having 5,000 and 6,000 and 8,000 data points to try to mull through. So you've gone from one challenge of not having enough data to really make good decisions to having so much data it's hard to extract the useful stuff from it. So we'll show you a little tool we've developed internally that helps kind of navigate that and filter out some of the important stuff. So curtain walls, you can define them in many ways, so broadly that you could talk about brick veneer and others. But for today's purposes, really we're just talking about sort of glass and metal cladding systems. Non-load bearing, non-gravity load bearing. They're supported by the floors, but they do carry wind loads. So this is pretty generic. This is a curtain wall profile. You know, this kind of extrusion profile has been around for a long, long time. If we talk about a standard profile, that's utilizing manufacturers' standard profiles, standard extrusions, using the tools that are available. Whereas a custom might be customized extrusion for a particular project, whether it needs to be curved or whether it needs to span larger areas, larger floor heights, or 2 or 3 stories and so forth. The erection type stick, there was a stick building going up not too far from my office in Burlington. I was a bit surprised they didn't use unitized, but so the stick framing is still used sometimes. Unitized is certainly the more common one now. It's been around since late 70s, early 80s, and a lot of that, I talk about extrusions and sort of that methodology, that hasn't changed an awful lot in a long time. The other, we could talk about that, potentially that's where a window wall falls into place. It is a unitized, it is prefabbed in the factory and shipped, but it's, the glazing method and so forth, kind of separate from a curtain wall proper. We often distinguish the curtain walls and window walls based on the glazing method. So an interior glazed, unitized panel, window wall is typically, we talk about that being an interior glazed system. It can be, the IGs can be changed out from the interior after the fact. It's not going to be rigging a swing stage to change, pull off snap caps and pressure plates and so forth. And typically we talk about that as being the, that single floor span. That's one of the things that distinguishes it for us as to what's a window wall, what's a curtain wall. So these are all sort of ingredients in our cookbook as to what a glazed facade can be constructed from. So here's an example that's just around the corner actually. So a curtain wall proper, it's hung from the floors. In this case, it can span a couple of floors, 2 or 3 floors because of its structural capacity. So different from what we would term a window wall, where it only spans a single story and typically sits right on the slab edge. This is hung from the edge on large discrete anchor points that gives you more flexibility for positioning. So one of the big advantages of that is that you've got much better adjustability for level and plumb and fit and finish control. Window walls, we've occasionally come across problems where there was tolerances in where the slab was poured both in elevation and horizontal, and you have some real challenges in maintaining sort of a nice smooth clean lines on the exterior just because of some tolerances with that. So the window wall can have that, for good or for bad, it's following the slab edge, and so therefore you can have some issues with it not being as true on the exterior as you would like. So that creates some problems both for appearance first of all, for performance. So you've got sealant joints that you specify at a certain dimension. You have through-wall flashing and water management details. When those tolerances change and those dimensions are larger or smaller, it can impact the performance as well as the appearance. So the very basic, the exterior batten, so the pressure plate, snap cap on the exterior. This kind of extrusion profile has been around for a long, long time. Still quite effective though. You can accommodate different. This doesn't have a structural thermal break. That's just like a rubber or plastic material. But you can modify this to accommodate a larger glazing gap there. So double glazed, triple glazed, etc. You can clamp in all kinds of different materials, insulated back pans, metal panels, stone facades even. So it's a very, very generic and flexible kind of system. So just a little picture of a sample we keep around the office just for to touch and feel and show our new junior staff. This is essentially the same extrusion profile, just sort of a head and shoulders profile. In this case, it's a wet glazed on the inside. There's our triple glazed IG. There's our pressure plate. Battery change, emergency on the fly. There we go. So there's our glazing pocket. So down in here, water that may get in past these seals can drain down. This corner block prevents the water from flowing beyond there, and then these drain holes allow water to get out. So one of my colleagues talks about curtain wall performance is really all about plumbing, right? Can we get enough water out of the system to be larger than the water that may come into the system? If we can, if our outflows can be better than our inflows, a lot of things work well. If that balance is off a little bit, and you get water accumulating, then it starts to impact whether that seal is good or it goes in through those joints and so forth. So this is the very basics of sort of a curtain wall proper. So you can see within this space, that pressure plate can accommodate, you can change that geometry fairly easily to put in different materials, different IGs. So here's a little bit more modern extrusion. So now we have a structural thermal break, which is of a different material. So a fiberglass or polymer of sorts. So now it's much, much less thermally conductive than this aluminum. So it could be on the factor of hundreds of times less thermally conductive. So now we have a much better temperature profile on the interior, on this surface here. So this is being warmed by the interior, and now we have something that is preventing that heat from flowing through there quite as easily. And those can come in different sizes, so you can have a double glazed, triple glazed. The beauty of the curtain wall proper is that you can also have these spacers and so forth to accommodate. There's your spandrel glass, and that can be standing off at whatever dimension you need, so that lines up a nice clean facade and still lets you glaze in your back pan, insulation, and so forth. So it's a very flexible sort of skeleton and framework to work from. It's very easy to glaze in all these different materials, and it makes it pretty easy to have good continuity of your air barrier elements. The challenge often comes where the curtain wall stops and some other kind of cladding begins, and did those guys talk to each other, or how do you make that connection? But the great thing about a curtain wall frame is that you can actually clamp in materials and make those transitions more flexible, both from construction sequencing and trades coordination. So the other primary glazing method is structurally glazed. So now you basically you can still have your same sort of insulated glass unit, but we don't have any mechanical fasteners here. We're relying on that silicone sealant to adhere the glass to the frame directly. And this can either be in two-sided structural, so you can have, say, your tops and bottoms, or your two sides. You can have pressure plates and drainage on two of your surfaces, or you can have four-sided structural glazing, where you end up with something like this, where it almost ends up being a face seal. You do have some potential for water to flow within there on that weather seal. Now this really becomes a unitized. This should be factory glazed, so you get good quality control for those seals, because that's everything for you now. It's your structural sealant. It can be prone to weather conditions and so forth. This is a very, very common system. The four-sided structural is becoming even more common than it was in past years. So how these guys get all put together before they get to site for a unitized system. A couple of pictures here of a typical glazing fabrication plant. So there's one of those unitized modules. So you've got large vision glass there. I believe that's a spandrel glass there. And so you can see the green is like a masking tape. So quality control on those structurally glazed elements is quite important. As I said, they're being relied upon for a lot. You have no backup from a mechanical clamping kind of system. So that green tape is masking. So now they're putting the sealant in there. So that's the typical fabrication. Here we've seen one where they've cut some back out, deglazing it for quality control purposes to see whether we've got good adhesion. So there's the finished sealant. So after they put it in there, they tool over it, make it nice and smooth and clean, ensure it's fully filled that, and they pull off the masking tape. So this is a finished location, pulling it back out just for quality control. So a little bit of the basics of that's kind of the mechanics of it, some of the basic materials. What does this thing really need to do to function, though? So, of course, we talked about controlling the separation between indoors and outdoors. So that's wind pressure, so there's some structural aspects. There's temperature, of course. Something that's going to become more important over time, as Dave talks about higher performance glazing and higher R values of the insulated glass units and other things, is the frame starts to become the limiting surface temperature. And so you'll have condensation on your frame potentially and not on your glass anymore. So those little microclimate issues are going to become more important. The surface temperature of the glass, when you have large IGs, you have a cold surface radiating, so it creates comfort issues. So just in the same way as you can have radiant heaters to warm a space without the ambient being all that warm, you can have radiant cooling as well. If you're sitting beside a large surface that's cold and it's radiating towards you, you can have thermal comfort problems. So those microclimate interactions need to be thought about as well. So daylighting, as we talk about higher performance energy requirements, we're now drifting towards that whole building energy modeling. So you have to consider within your glazing design, can you take advantage of daylighting? Reduce your lighting loads and save some energy there, or is that going to be a problem where you've got so much so much vision glazing that you get hot spots and overheating and some of those solar gain problems. So talk about ways to take advantage of that and to offset the negatives of that. So I talked about aluminum being highly thermally conductive. If we look at a temperature profile through a typical aluminum framed window, the colors here represent the temperatures in Fahrenheit. So 0 on the exterior and 70 on the interior roughly. You can see that the color, the aluminum, even in here where that's a thermal break, you still have temperatures on this interior surface of that aluminum that are potentially below freezing. So if you talk about critical temperatures, you've got a glass surface and you've got a frame surface, those are going to be the locations where condensation forms. So for a standard sort of run-of-the-mill aluminum extrusion, you can have very cold surface temperatures right in there. And 0 Fahrenheit is essentially minus 18 Celsius. It's basically the Toronto winter design temperature. So this is a practical example for our location that you can get temperatures like that. Compare this to a fiberglass frame where now it's been formed into the same kind of profile, same shape, so that you've got all of your other kind of standard materials and components can still work in there. This fiberglass pressure plate is actually one of those minor upgrades in a standard aluminum system like this. You can have some big bang for the buck. It's only substituting out one little component of it, but it's less thermally conductive and it can have an impact, a positive impact on that. But for this, we're looking at sort of just substituting out aluminum for fiberglass, and look at the difference in the temperature profile. The surface temperatures on that frame, where that might be the exposed surface on the inside, have now gone all the way up into the 60s somewhere. So now we're easily above plus 10 Celsius. So that's now above the typical interior dew point temperature for winter conditions. So you've now pretty much eliminated those condensation risks on the typical interior. So this is really just looking at sort of condensation risk, but of course there's going to be a huge energy benefit from that reduced heat flow out through the system. So that's a little bit of energy and microclimate kind of combined. You can also utilize wood as one of your framing elements. So the wood is your structural component. So the size and depth of that gives you whatever span is required. You can have that a single floor span or more than one. We know of a firm in Ottawa that fabricates wooden curtain wall frames with these aluminum componentries here. So the nice thing is that all of that sort of glazing componentry is all standard, off the shelf kind of similar shapes, similar profiles. You can choose whichever one of these you need for double glazed, triple glazed. You can have the exterior caps also be wood for appearances, but it's also much more thermally efficient than having it all being aluminum. So both more so for aesthetics has been the primary driver in recent years, but you can imagine if from the green perspective and from from a materials usage standpoint, if carbon footprint and carbon credits ever come into play, the carbon footprint of that wood compared to aluminum is vastly different. And so if the cost of this is probably higher than aluminum, but if those costs are ever equalized for the carbon issue, then the wood will become much more economically advantageous probably. So you could suddenly have a much larger share of the market because of that. So those are the frame elements on the glass component. Vacuum insulated glazing. So you see these little dots here? What they are essentially is little beads of glass that separate two sheets of glass. So you have two sheets of glass that are separated by a very, very small space, which is evacuated. So they draw the air out of the space between those, and then they solder the edge of the glass. So what you end up with is what almost looks like one sheet of glass, but it's actually a very small insulated glass unit. And so there's no air at all within that space. You're not talking about the difference between plain air and argon and any of those kinds of things. It's actually completely evacuated. And if you look at an infrared image of this glass, it's very interesting because you see these little tiny dots, because those are sort of mini thermal bridges where there's no insulating value right at those spots, but those are only a couple of millimeters in diameter on a large IG. So what they do essentially now is you've got one sheet of your glass that you can put into an IG has much higher performance. So here's how you might utilize that. So right there is actually one hard vacuum insulated glass unit. Essentially, it's the same thickness as the other pane of glass, but that element by itself has a higher R value than the double glazed IG on its own. So now you put one component into that overall piece, it can make quite a large difference. So comparing looking at some therm models here, these are just sort of temperature profiles. So a fairly standard structurally glazed, double glazed IG with structurally glazed finish and insulated backband. And you sort of look at the temperature profiles. Again, looking at these critical temperatures. So for this, very kind of run-of-the-mill average performance, you can have a 38-degree surface temperature at the edge of the glass and 40 at the frame. So we're talking single digits Celsius, 5, 6 degrees potentially. So pretty big risk of condensation in most environments. If we substitute this out with just simply changing this spandrel glass to a vacuum insulated panel, which we'll show you in a moment here, some of the details of that. But the R value of this now jumps up significantly from this, and it also changes the profile of where that insulation happens. So changing out just one component makes a huge impact on the surface temperatures above. Or comparing our hard vacuum insulated glass unit glazed into a double glazed element, comparing that to the performance of a triple glazed element, you can see that this double glazed, essentially the same size, same components of a double glazed IG, has a much better performance even than a triple glazed IG. So this and this would be significant cost upgrades, but significant performance upgrades. So Dave's going to talk a little bit about where and when to use those, where's the value, you know, where's the payback and some of those things. But in terms of the performance upgrade, to go from 38 to 60 means a huge difference in the kind of occupancy that you can accommodate. What sort of relative humidities, what sort of environments and occupancies, and what sort of payback on thermal comfort. So being able to have workstations and activities sort of closer to the glass in some cases. Now, something that has hit the marketplace a little bit, I think that, that a form of this has actually been installed at the new Humber River Hospital at Keel 401, is for the glass itself to be controllable as a shading element. So instead of having, you know, internal shade elements in traditional windows, and you sort of, the ability to control daylight coming through there is essentially you go from all to nothing, and you lose all of your vision, lose any ability to see out through the windows as well. Whereas the dynamic shading, it can go down in very small increments, and you still maintain some ability to see out through the windows, see the landscape. This is all driven by high-performance chemistry. These dynamic elements are essentially, they're multiple layers of ceramic materials, very thin. The total thickness of the 5 layers combined is still only, you know, a quarter of the width of a human hair, but a very small voltage across these changes the interaction of those 5 layers and essentially keeps decreasing the transmittable light through them. So here's a real world example. This building's in California. So typical IG's up here and this dynamic glass down here. And you can actually see a little bit of the variation from quite dark down here to a little bit more light passing through to, you know, to uncontrolled light coming in through here. So one of the issues that they're trying to control is the solar gain coming in at floor level, where it would be a lot of glare, it could be a lot of localized heating, solar heat gain. So this foyer could become quite uncomfortable with the heat that's passing in through these windows. So this is primarily a solar heat gain and overheating kind of control, less so than a vision control. Now this one is a little bit different. Same kind of technology in the glass here, in a very large kind of skylight. So this multi-use space, here they do want to control the daylighting a little bit more. It's not primarily about the solar heating, but it's a very large space. So just kind of showing the renderings here of how the space can change, both, you know, so the look and feel and functionality of it. So even in the middle of the day, you can darken that thing quite a lot. So great options for designers, for architects to have a large communal opening space like that, but also control it so that it's comfortable and usable at all times and sort of all outdoor conditions. So those technologies are great for sort of controlling how much light passes through. What if you really want a lot of light passing through, but your biggest concern is, you know, is localized glare and hot spots and things like that. So there are a number of technologies for light diffusing glass. So this one, as an example, has fiber optic filaments in here that are positioned perpendicular to the glass. So the concept is light coming from the exterior can hit that glass at any kind of angle, but because the fiber optics are positioned perpendicular through the glass, that they're only really transmitted through that space perpendicular to the IG. And so when they exit the other side, they're now coming out perpendicular to any of these. So the light's coming in at different angles from different directions. And so what it does is sort of that passive lighting. So the light coming in here is essentially coming in horizontal, sort of along that roof line, and then now it's bouncing off all these other elements And so you get this nice kind of diffused lighting in the background. So this is the software simulation from this firm here. It shows you the typical kind of problems where you get some daylighting, but it's very concentrated. You get a lot of glare in these areas, and you get very little light in other parts of the building. So you can see that's a gable end, where essentially it's the light coming in from there, and depending on the time of day and the angle it's coming in, it's lighting up the wall, it's not lighting up the floor at all. So changing out all of these IGs with the light diffusing IG essentially transforms this space into this kind of a background lighting profile. So huge benefits for your lighting costs, for natural light, and it takes away some of your issues with your localized hot spots and cold spots. So back to a more traditional, sort of the past and present. A light shelf is actually quite a very old technology. Frank Lloyd Wright used it in a lot of his buildings in various ways. Typically, he used large structural elements, projecting floors and awnings and balconies and so forth. But the simple concept is that this shelf shades the space below a little bit, allows the outdoor light to bounce off of it and sort of diffuse into the ceiling space. So curtain wall manufacturers and others have now been building those things into their componentry. So in this case, it's a shelf on the inside of the building. In many cases, you can do the same. The outside will just be sort of an oversized snap cap system that essentially you've created that sort of reflecting shelf on the outside. And so it tends to bounce the light in up here and diffuse out in the same way. To make even more use of that is this is a very passive approach. Now, a more active approach is you actually have controls. So you have these elements that you can extend the size of your shelf. You can move these in and out. So at certain times of the year, you don't want any shading. You want solar gain in the winter. In the summer, you want the light, but you don't want that glare. So these elements are actually controllable and can maximize how much light is redirected inside the building. So taking a passive system from years past and optimizing it a little bit more with some more active controls to it. So the vacuum insulated panel that I referred to in one of those earlier slides where it was glazed into an insulating glass unit. This is a technology that's been around for quite a while. Essentially, it's a silica core. It's essentially sort of like a honeycomb system where there's a lot of voids, and you wrap that core with elements that you can then evacuate. So you pump all the air out of it. So you have an almost perfect vacuum in there. So what that does is take that 1-inch insulation layer and transform it from an R3 or 4 to an R40 almost per inch. The real problem in the past has been that this is very, very fragile. So you puncture that film and you go from 40 back to 4 or 3 or 2. So it's been around quite a while. The innovation has been how to utilize it in an envelope system in a way that it can be durable, it can be functional. So an innovation recently is to take a panel like this and seal it into an IG. So put it between those two layers of glass, seal the edges like a typical IG, and now you've got a very, very high performance element that's protected, it can be durable. So as an alternative, say, to spandrel glass, instead of a back pan and all of that, is put an IG with a vacuum insulated panel glazed into it, into that system. And that's essentially what we've got right there. So you can have something that's, again, it's almost the same size. It's very easy to glaze. It's something that's very easy for the standard erection and fabrication methods. It's not something that really drives a lot of cost from that fabrication erection side, but it gives you a huge bang for the buck from an energy perspective. So that's one of those innovations that we're seeing enter the marketplace now. It's still a little bit cost prohibitive in some cases, but as Dave talks more about how we satisfy those energy codes, especially as 2017 approaches, this is going to certainly be one of those tools in your toolbox as designers. So this is just another manufacturer, but a similar product. You got that high performance core. You got this skin around it that you draw all the air out of it, create a vacuum, and seal it off. And so there's your effective R value per inch. So in this case, 39 compared to most of the other insulations. So again, if that gets punctured, it gets damaged, that goes down to the same levels. Some of these are actually better as well now that the core is a bit less prone to that it doesn't diminish all the way down. So the technology even of the core itself is getting better. But if you can protect it, put it in an IG or some other system like that, you now have something that's durable. You can rely on that R40 for the same lifespan as an IG or even longer. So those were all sort of standard IGs or products. This is relatively different in that sense. This is aerogel? Calwall. So this one, this is some sort of semi-translucent, so you can still get a little bit of daylighting in a very, very high performance element. So just another tool in the toolbox. So I gave you a little bit of the background, sort of where we've been, where we're headed, some of the materials we might utilize. I'll turn things over to my colleague Dave now and talk about some of the whys and hows of why would we use a hard vacuum insulated glazing unit and what the challenges might be and some of the issues that are coming up in the future. Dave?
Hello, everyone. Thank you. So hopefully this next part of the presentation is the fun part where we start looking at energy modeling and all these different scenarios. Steve obviously wanted to make sure that you guys have that we're all kind of on the same page in regards to the basic functionality of curtain wall systems and some of the different products that are available. Before I start my comments, what's always helpful for me is to have a good understanding of who I'm speaking to. So I usually like to start off by identifying the different sectors that I'm dealing with in the audience. So from a show of hands, how many people are owner developers? Okay, so we got some good contractors. Okay, some good representation as well. Architects. Okay, the architects are winning the room right now. Consultants. Okay, so you're gonna have tough questions for me. Okay, nice. Oh, great, so that's good. So we've got quite a mix of different people. What I'll try to do is make sure I touch on, some of the different concerns or interests based on the industry that you're in. So what I'm going to do is talk about energy. Obviously, one of the big reasons we're all here is because, I'm sure through all your project experience, you guys are encountering the challenge of, how do we continue to build these beautiful, elegant buildings with glass, but also continue to meet the high energy targets that we need to meet and that are increasing on the buildings that we all design. So let's talk a bit about the energy regulation, status or current situation in Ontario and in Toronto right now. So obviously, energy code is governed by the Ontario Building Code, Part 12, Resource Conservation. Within that, it refers to SB10, which is Supplementary Standard SB10, which essentially governs the energy performance of all buildings. Essentially, within that supplementary code section, there's essentially two paths for you to comply with energy code. There's a path associated with performance. So essentially saying, my building performs in a certain manner compared to a reference building. So you model your building and say, that I'm meeting a certain target above the reference building. Or essentially a prescriptive path where you're following fairly strict requirements. Typically for high performance buildings, the compliance path isn't, prescriptive path isn't selected because there are restrictions such as glazing ratio. So for example, a 40% glazing ratio, which I'm sure wouldn't apply to a lot of the buildings that you're probably here wanting to know about. So buildings that typically have high glazing ratios but also want to be green, right? Those are a lot of the kinds of buildings we're seeing in high-rise office buildings in Toronto or institutional buildings. So those buildings don't typically lend themselves to the prescriptive approach. You typically have to model the performance. So again, just to identify what those actual targets are and a bit more nuts and bolts. Essentially what those targets are is that you can either comply by performing your building or your project-specific building performing 5% more energy efficient than ASHRAE 90.1 2010 or 25% better than Model National Energy Code 1997. And recently there was an adoption of a new path from a performance perspective, which allows you to essentially meet the National Energy Code for buildings. So, it's a bit of there's a lot of options right now. There's a lot of debate within the modeling community. I'm not a modeler. I work with our modeling group to help apply those technologies on projects. But essentially, what's going on is that, ASHRAE is an American standard. Model National Energy Code for buildings, 1997, is the Canadian standard, and then the 2011 is the update to that. But for various reasons, the codes haven't decided yet to get rid of 1997, and I'll explain a bit more why that is as I continue in the presentation. So to add to the confusion, to add to the challenges, really on top of that in Toronto, you're also dealing with the Toronto Green Standard. So obviously a city-focused initiative to say that if you're going to build in Toronto, you need to meet certain performance targets. Prior to January 1st, 2014, essentially the targets were the same for Tier 1, which is the first level, which was a mandatory level for the Toronto Green Standard. It was the same as the Ontario Building Code. That's recently changed. So January 1st, 2014, so this past year, that target was actually increased by Toronto City Council. So we have a more aggressive energy target now in the City of Toronto than the remainder of the province. So let's look at that a bit historically. Hopefully you can track with that. I'll try to take my time to explain this. So what I've done is I've essentially tried to compare all the different iterations to all the same baseline, so you can see the progression or the increase in targets. Blue represents SB10, so the Ontario Building Code. Red represents Toronto Green Standard Tier 1, which was the mandatory requirement. You have to comply with that level. And then Tier 2 is an optional standard where essentially you get rebate incentives. But those rebate incentives are very robust. So in my experience, a lot of projects are pushing very hard to try to achieve Tier 2 because developers and the owners who are essentially sponsoring those projects want to recoup those incentives. So what you'll see is in 2013, where you would have been is for Ontario Building Code. Again, you needed to perform 25% above Model National Energy Code. And like I said, Tier 1 essentially was that same standard, which was, again, these were both mandatory. Optional, if you wanted to get rebates, was essentially on your development fees, was 35%. So that was the situation in 2013. 2014, like I said, the Toronto Green Standard, which includes Tier 1 and Tier 2, was increased. So this past year now you were at, to comply with building code or comply with the Toronto Green Standard, which was mandatory, Tier 1, you had to actually now perform 36%. What I think is important to note about this is that the current mandatory standard right now at Tier 1 is what used to be essentially, for lack of 1% difference, essentially the old Tier 2 standard. So why I bring that up is to say that the new minimum mandatory standard is what used to be the optional standard. So obviously there's a significant push, specifically in cities like Toronto, to really push the performance of buildings up. And Tier 2, you're now at 44%, which is, I'm going to say, is very difficult when you're talking about highly glazed or, high glazing ratio buildings. So, these are not targets that are easy, and really, for lack of a better word, what I'm seeing in the industry right now is we're really starting to hit a tipping point where, before the increments of the code and energy efficiency, we had the tools in our toolkits to essentially manage on projects. We're starting to get to the point where now, we're running out of effective tools to really get us to those energy levels. So I'll start talking about how I see the industry responding to that. So last is 2017. So in 2017, the Ontario Building Code is going to be updated to essentially push all of Ontario to 35% above Model National Energy Code. So obviously it's not just Toronto, the Ontario government, the federal government, and it's estimated that buildings consume about 35% of the energy in our overall economy. So obviously as as governments struggle with how to deal with climate change and how to deal as well with reducing our dependency on, various energy sources, there's a big push on in the building sector to see some significant improvements in performance, similar to the auto industry. So last is tier, the question I often get asked is, well, what's the crystal ball? Where do we think this is ever going to stop? So there have been some studies done in the past, and it's estimated that in order for a building to produce through renewable sources, solar panels or some sort of other source, to produce all the energy on site that it consumes, that building has to be roughly 65% better than Model National Energy Code 1997. So a net zero building is about in this range. So why I illustrate this is in 2017 the code's going to change again. But to get from 35% to one day eventually 65% is still a big jump. So, why I highlight that is that, don't expect that, the next code iteration is going to be the final iteration in regards to pushing energy performance. So again, as an industry, we're going to have to really figure out not just how we adapt to the next code, but how do we adapt to the next, 15 to 20 years. I'm sure all of you are going to want to be practicing for the next, 10, 15 years. How do you integrate practices how do you integrate approaches through your projects that'll help you deal with those, increasing challenges in the future? So again, like I said, Tier 2, which is the optional standard, not mandatory, obviously now is a very aggressive target in the City of Toronto. You're talking 44% better than Model National Energy Code. That is by far not an easy target to achieve when we're talking about highly glazed buildings. So a bit why that is. So this is Sustainable Buildings Canada. Did a study for the Toronto Green Standard to help validate, what the correct targets were for City Council. As part of their study, they used various archetype buildings. So I've borrowed this from their report. One of the archetype buildings that they refer to is a high-rise office tower. So that consists with a lot of projects we're probably talking about when we're talking about curtain wall projects, high-performance curtain walls. It's office towers and institutional projects primarily. You'll see in this building that from a facade perspective, obviously your facade energy, as in your enclosure, how it connects to your energy pie is through space heating. So essentially, you're paying good money to condition with your mechanical system, exterior air to the interior, and now what you want to do is retain that energy by having an efficient enclosure that doesn't permit energy to simply just transfer back out to the exterior. So obviously space heating is directly connected to the performance of your enclosure. So the better your enclosure, the less your space heating cost should be, because the more you're able to retain that energy in your indoor space. So obviously, as you see for a high-rise office, that 37%, roughly, of energy use is related to space heating. So that's a significant part of the pie. So if you have a poor performing envelope, which, obviously glass, you're talking about an R3, that's obviously going to have a big impact on, on energy performance for the overall building. I think the other thing to note as well is that not only are the targets increasing, so like I said, targets are getting more strenuous, but actually reference buildings are getting better. So the example I often use is, a 1997 Toyota Corolla is not as fuel efficient as now a 2011 Toyota Corolla. So we've actually, the technology that's now commonplace for cars is better in regards to fuel efficiency. So similarly for buildings, right now in a lot of design projects, we're often comparing our projects or our buildings to a 1997 building, which has 1997 electrical systems, 1997 mechanical systems. So what was considered baseline or what was considered normal systems at that time are not what would be considered normal systems now. So not only have the targets increased, but also in the new code, the 2011 National Energy Code, you're actually seeing a higher performance building, a much better baseline. So the gaps that we're seeing, where we used to be able to take a lot of, we used to say, well, my envelope's only performing at about an R3, but I'm going to invest in much better mechanical systems, much better electrical systems, and there was a lot of trade-off there that I could now trade off against my poor performing envelope. you're seeing that gap actually diminish. So actually, the mechanical systems that are assumed as your baseline systems are more efficient, and the targets are increasing. So, the bar is moving on us in two ways. So obviously, a part of why you're here at the seminar is to understand, well, what's the benefit to all this? Why, again, all the push towards energy efficiency? Like I discussed before, obviously, climate change, energy security, all these high-level political issues affect our industry in regards to the governments wanting to see more improvement, better performing buildings. So for an owner-operator, I mean, obviously the biggest benefit is ideally lower operating costs, so lower utility costs over the life cycle of your building. For actual people, obviously in a lot of these buildings, typically if you have higher performance buildings, you also typically have buildings that are more enjoyable to use and to live, to work, to play, and to do all the things that we need to do in indoor environments. Obviously, the disadvantage to this push is that it requires significant capital investment. It's just more expensive to build higher performance buildings than it is to build typically poor performance. Now, not everyone will tell you that. I will tell you that. Some people want to try to say, well, it'll cost the same, and and that's hopeful. But typically, in order to build a more efficient building, usually at the very least initially, until those technologies become very commonplace, there's more capital investment to build a better building. The big other challenge for our industry is that as you build better buildings, it means really starting to adopt some new technology. So again, Steve brought us through what I call the buffet of options, like wood framing for curtain wall systems versus fiberglass to the current aluminum, different types of insulated glazing units, vacuum insulated glass, vacuum insulated panels. Obviously, these are not technologies that have a track record currently right now in the industry, in being installed in buildings. So therefore, obviously, as architects, for example, or as contractors, there's more risk inherent to installing those new materials on projects in regards to, how are these really going to perform in the next 15 to 20 years? Am I gonna design it in a way that's going to encounter a problem and increase my liability? Am I actually, have I been able to properly mitigate my risk? And obviously, with current practices, there's a lot of performance history that we can draw on when we're working on project teams to say, what's the right approach, what are the right details, how do you make sure you build the facade correctly. But when you start using different materials, you don't necessarily have the benefit of all that performance history and other people's mistakes to rely upon. So again, a bit of a summary of energy regulation. Basically, some takeaways would be that energy regulation is getting stricter. Like I said, the targets are moving up. Not only are the targets moving up, but also the buildings that you're comparing yourself to when you're modeling your building versus another building. That base building is more efficient, like I said, so two targets are moving on you at the same time. So again, what used to happen, which was a trade-off typically, that's becoming increasingly difficult. So really, typically you are having to make improvements to the facade, because now the facade tends to be the component of the building that's dragging the energy performance down. So again, we'll talk again about predicting performance. So again, typically what happens in projects, or the traditional approach, is that the design development will happen, the massing of the building will be identified, basic structure, basic types of components, and then essentially there'll be some energy modeling that happens to say, okay, how is this building likely to perform? Well, the challenge with what I would call now the fairly typical approach is that at a certain point, once you've gone a certain distance in the design, once you've identified basic things like how I want the building to look, you've really also identified things like glazing ratios. It becomes really difficult to change aspects of the facade if you need to meet energy targets. So if you're not careful, when you're talking high performance buildings, if you're using this traditional approach, you can often get to a situation which, I am often dealing with this on projects, where where too many design decisions have already been made in regards to the envelope, such that it's almost impossible for us to reach the energy targets for the building, or the investments now required in other components become completely prohibitive. So I think what we're going to see more of in the industry is a different type of approach when it comes to energy modeling, or a better identification of what the options are prior to getting into a detailed design of the building, so that we make sure we're on the right track. You know, what's the right track so that we actually get to the energy target that we're shooting for. So we've thought a lot about this internally as to how do we at an earlier stage in the process, how do we as a design team, or with our design team, have a better sense as to all the interconnecting components and how they influence each other. So obviously in a project, you know, you have your energy target that you're trying to meet. You also have a certain type of HVAC system, a certain type of lighting system. You also have a lead rating system you're trying to achieve. You need to achieve a certain amount of points. And really all these things we often view as separate components. And what we will do is run a model, and then we hope for that all the pieces kind of fall into place, and then we tweak to kind of put them all together. But obviously, increasingly, as the targets are getting stricter, that's harder to do. Really, what you want to do as an earlier stage is you want to be able to see how those components are connected. So what we did is we started looking at how do we make that more visual? How do we make those interconnections visual so that we can make better decisions in the design process? This is just a diagram that we created to kind of illustrate the concept that you could actually visually look at energy use in a building and visually connect it to different components. So based on this kind of proof of concept, we built a mapping tool. So we did this internally through our modeling group, which, you know, they're phenomenal. I give them great praise for putting this tool together. So essentially what this tool does is at a very early stage, we would run 5,000 scenarios, which sounds like a lot, but you know, it's doable. You run 5,000 different scenarios based on all different parameters of a certain building. So going from a glazing ratio, so for example, going from a glazing ratio of 80% all the way to 40%. And for your project, you can do different types of mechanical system, what I call like a base level code compliant mechanical system, or a higher performance mechanical system. You can also figure out, you know, your amount of lead points. And essentially what you'll start to see is once you do all those models, you can essentially plot the data. So now, like Steve said, you have 5,000 different models you've run. It doesn't need to be 5,000, but let's say you've run 5,000. You have all this different data. The question becomes, how do I make sense of this data in regard to what's my path to the energy target and to the other targets I'm trying to achieve? So what we did is through this mapping tools, we essentially will extract that data and then map it visually. So we'll plot different axes that are important to the project objective. So in this specific project, we plotted heating efficiency, so mechanical system. We tried to simplify it by essentially, like I said, only really having 2 levers for the mechanical system. Lever 1 was a typical code compliance system. Lever 2 was a high efficiency mechanical system. Different lighting intensities, different glazing ratios, and then again, from a window perspective, we tried to bucket it to about 4 different options, which were essentially, you know, code compliant windows, the best, you know, double glazed IG curtain wall system you can, you know, essentially you can buy. So, you know, double OE coatings with the glass and argon filled, and, you know, good thermal breaks, a unitized system. And then essentially, okay, triple glaze, and then best triple glaze. So again, better glazing, better thermal breaks. Then again, lead points, and then energy performance energy performance. This axis goes this way actually, so above ASHRAE 90.1. So at first you'll start out with a lot of data. I know for you just seeing it right now, that won't make any sense to you. It would be very difficult to actually visualize. It takes some practice, but we found this really helpful for ourselves internally so that we have a good sense as to where are the actual design decisions. So what you can do is start to say, well, let's take out extraneous information. So now I have all this data. Now really what I want to do is sift out all the data points that don't work. So all the data points, for example, Failing my lead requirements is not really an option, so let's just sift out all that data. So what you can do is start, like I said, sifting out data. So we started from, okay, I at least need to pass lead, as in I need to at least meet the minimum target in lead, which is you have to perform a certain level above energy, which I think the minimum credit is 10%. And then from there, as I get more energy performance, I'll get more points under lead. So minimum is we need to at least comply with lead for this building, and ideally I'd love to get 6 points. Similar to energy performance, obviously we need to perform at least 5% better than ASHRAE 90.1. So anything below that's not really an acceptable target either. And then for this building, we knew from a cost perspective that it was going to be cost prohibitive to go towards a triple glaze system, that was just going to be such a cost to the building that it was very unlikely that that would be selected almost under any situation. So we sifted out that data, at least for an initial review. And then glazing ratio, again, we knew that we wouldn't be able to get below about 60%. So what that helped us do is at least sift out all the data points that are essentially they're deal breakers. There's no dice. We can't do those. They don't work from a perspective of basic requirements of the project. But what that does is it starts to at least outline for you what are the paths that help you achieve. So if you follow these lines, you can see this line as, for lack of a better word, this is your roadmap as to what you're going to have to do in order to achieve your target. So for example, none of the roads lead to a code compliant, simply mechanical system. All the roads lead back to a high efficiency mechanical system. So we know that. So now we know for sure that this project's going to have a high efficiency mechanical system. But now what about the facade decisions, which will have significant impacts, and which, if we design the building, as in if we illustrate completely the building and all the glazing ratios, it's going to be very tough for us to change that. So what we do see is actually there's really two paths. There's either a path at 60% glazing ratio or higher, or a path at 60% glazing ratio or lower, or 70% glazing ratio or lower. So why that's important is because often what I will, on a project, we can be discussing, okay, let's try to reduce our glazing ratio by 1 or 2%. But the question is that 1 or 2% actually going to make a difference for the targets you're trying to achieve? So for example, for this project, if we are at 66%, reducing another 2%, although it saves us some energy, it doesn't help us achieve any of the other targets. It doesn't move any other targets, either lead points, either getting a different type of window system. So then visually we can tell to ourselves, basically the two parameters is either you're going to have to be at 60% or lower, or 70% or lower. And that being at 68% is pretty much the same as being at 60%, which is actually really helpful information, because we know really that our target isn't 61% versus 62% versus 63%. The targets are really 60% or 70%. So that information is actually really helpful at an early design stage, so we know what we're shooting for in regards to the appearance of this building and the facade. What you'll see as well as we continue to sift out information is what I did is I sifted out essentially simply a code compliant window. I said, well, because I essentially said that, well, let's really look at sorry, pardon me, actually, no, for this iteration, what I did is I sifted out the lead points. So here, the bare minimum was pass. But I said, okay, well, as we're talking with the energy modeler says under optimization of energy, we're going to need at least 2 points, right? Let's say, for example. So then I can sift out these options because I know they're just not feasible. We need a minimum of, let's say, 2 points. So I can sift those data points out. And again, it highlights to you key parameters. So for example, now by needing to achieve 2 to 3 points, you automatically now it's no longer feasible under any scenario for you to use simply code compliant windows. You're going to have to use at least a best double, as in at least a high performance double glaze system. It also allows you to identify that an 80% glazing ratio or anything above essentially 70% is not feasible to achieve this target. So now you can visually connect, okay, before 80% would have gotten you to a pass or a 1 as a road option. So 80%, you could go down to a double, and then you could get to a pass or potentially get to a 1. But as you sift out the data, you see that this road no longer exists. Only road options left to you is either, again, like I said, 70 or below or 60 or below, which both lead to a double and gets you to 2 or 3 points. So again, if you can drill down further of, okay, I know for sure now I need 3 points. Well, here's your roadmap. This is the only road that leads to Rome. So high efficiency system, lighting needs to be at about 0.7, 60% glazing ratio, high performance double glaze system, and then you'll get to about 3 lead points. So this kind of information is really helpful so that in the midst of design process, we know what we're shooting for. We know that, because often what we'll have is we'll have all these moving parts as to, okay, how efficient our mechanical system and how efficient can I get the lighting, and everyone's just trying to do the best they can and hope that it'll all fit together, which increasingly for high performance buildings is a strategy that tends to get us where we're not meeting targets, or we're not meeting, instead of getting LEED Platinum, which we had shot for, now we're getting LEED Gold, or instead of being able to meet Tier 2, we're not able to meet Tier 2, which becomes obviously very problematic in regards to project progression. So now that we've talked about overall energy, so some of the what I call doing all this type of whole building energy modeling and then plotting all this data and making interconnections so that we can visually see what our options are. I mean, the old adage still applies, garbage in, garbage out. So what you need to do, or what energy modelers need to make sure, is that the inputs that they're providing for the facade are accurate. So we've done a lot of work. I mean, energy performance through building components is still an industry that is, that there's a lot of debate, a lot of lack of understanding. We made significant investments in this field about 5 years ago. So essentially investing in three-dimensional heat transfer simulation. So we partnered with ASHRAE. Morrison Hershfield was the principal investigator for the ASHRAE 1365 project, which I'm hoping people in this room are familiar with. It's fairly common now. It came out in 2011, so a lot of people in the industry are aware of it. Essentially, that was a research project where 40 building envelope details were cataloged compared to hot box measurements, compared to modeling simulation, where we did the modeling simulation and calibrated our model based on the actual hot box verification, so that we knew that we had very accurate data. So, and we knew that the model would provide accurate results because we were able to calibrate it against actual real life hot box simulation. So that came out in 2011. There was lots of things we learned from that. At that time we had thought certain performance from spandrel sections, through 3D modeling, we actually, found out that it was lower than we anticipated. Similarly, window wall systems, there were lots of implications for that we identified. And also things like, typical building construction elements like shelf angles, cantilevered balcony slabs, a lot of those elements where there was a lot of debate in the industry about how big of an impact that has on a building. We were able now to quantify that impact, and for certain buildings in certain situations, it made a fairly significant difference. So back then, three-dimensional heat transfer analysis, the traditional approaches when you had a heat transfer issue in a building, we're saying, okay, you can do hand calculations, which are extremely onerous. You can do lab measurements, so hot box testing, but obviously that's significant cost investment. Or you could do computer simulation, and the most popular program would be Therm to do two-dimensional heat transfer simulation. The challenge with using two-dimensional heat transfer simulation was that often it didn't account for lateral heat flow. So obviously, you can have heat not just transfer in that two-dimension section, but interact with other two-dimensional sections, which will actually change the appearance of heat flow in that two-dimensional cross-section. So basically, it's a three-dimensional world, not a two-dimensional world. Trying to use two-dimension to illustrate heat transfer through 3D components tends to be very problematic. You have to make a lot of assumptions, and then those assumptions are very much open to debate. So again, we moved to three-dimensional heat transfer. That's why we did the ASHRAE research project. Since those humble beginnings of 40 details, we recently published a new guide with the partnership of BC Hydro, so the government of British Columbia, Homeowner Protection Office, and as well some other partners. So from 40 details now, this new guide has hundreds of details. I haven't counted the exact number. It's over 200, I believe, but hundreds of different details. So before the criticism of ASHRAE 90, not ASHRAE 90.1, but ASHRAE, the ASHRAE research project 1365 was that, no, there's only 40 details. How do I connect this to my project and to the details we have on our project? So now we published a new guide which has hundreds of details, probably covers your project. And then the new criticism is, the guide's too big, there's too many details. So I'll give you a link to where you can find this, this guide, but essentially it covers a bunch of glazing systems, which before in the old research project we hadn't covered extensively curtain wall and window wall and some of those other glazing systems. So reason why I brought you through that is to say that essentially when it comes to understanding heat transfer through a curtain wall system, and therefore what are the things that I can do to improve the performance, you first really need to make sure you understand how heat transfer happens through building components, which you know, sounds easier than it can often be. So when it comes to when it comes to a curtain wall system, I mean, really oversimplified, the two locations where you have heat flow is through a spandrel section or either a vision section. Obviously, IGUs, technology of IGUs has significantly improved in the past 20 years. You know, there's lots of options such as low E coatings, changing the air from air to argon, changing the spacer from an aluminum to a warm edge spacer, which has significantly improved the performance of insulated glazing units. Spandrels were a more difficult one because one, obviously, IGUs are manufactured by the glass industry, so it was relatively easy to improve the performance and that be integrated into systems. Spandrel sections were much more proprietary in regards to different manufacturers and did pose some challenges in regard to, well, what are we going to do to make our spandrels better? So the typical approach was really either put insulation in a back pan or put insulation on the backside. So as part of the ASHRAE research project, we did model three-dimensional heat transfer through those types of assemblies. So the first image shows you the traditional spandrel section with insulation in the back pan and essentially a slab edge and steel stud infill wall. And then as well, we modeled, well, what if we do spray foam on the backside and spray foam as well in the stud cavity, which is the common approach right now if you're trying to improve the performance of a spandrel section for a curtain wall system. So these were some of the results, which again, these are the inputs that you would put in an energy model so that you properly understand how those interconnections from a perspective of overall energy. So that's why I'm going to great length to explain why it's really important that you understand and that you have correct inputs. So for this shows you a graph between the interconnection. So from the perspective of the back pan, the bottom section is where you just have a stud cavity that has air, so just insulation in the back pan. As you can see, there's only so much insulation that'll make a difference. Once you get to about R25 in a back pan, it really doesn't make any difference because you have so much heat transfer through essentially around the spandrels, around the spandrel section. And then similarly, spray foam, pretty much under all situations, added about another R4, but again has limited impact because again all the lateral heat transfer around those assemblies. But I mean again, not an insignificant number. Basically you can get with some spray foam insulation, you can get to an R9, which is a pretty decent value in regards to thermal performance for a building. My rule of thumb is usually at about R15. The energy performance of the building becomes less consequential. I mean, that's my rough rule of thumb, but it served me well in regards to having a sensitivity analysis of, at what level of performance is my wall have enough insulation that typically from an energy perspective, it's no longer the driver of performance, and that's been my rough rule of thumb. So again, the question becomes, well, how do you move spandrel sections to the next level? So what we've done is looked at vacuum insulated panels. So again, like Steve said, that's by far the most promising technology to really see improvement and change in the performance of a spandrel section. So vacuum insulated panels, obviously from our value, are 40 per inch. That's significant amount. We modeled various different scenarios actually in the guide I showed you before. So situations like a conventional curtain wall, unitized, high performance, where you'd have a larger thermal break and window wall applications. We also did all sorts of applications of the vacuum insulated panel. Again, like Steve said, what we've seen as the most constructible and the one that has had the most adoption or the most potential in our opinion is when you essentially put a vacuum insulated panel in an IGU. So, you know, that's more like from a constructability perspective, it's easier because it's almost like it's still just glazing to a lot of the installers. But now instead of in just glazing an IGU, you're actually glazing in an element that has a much higher thermal performance. And also it protects the vacuum insulated panel. So we've seen that as what I would call the technology that's most adaptable and likely to being incorporated into buildings first as we start to push from an energy perspective to higher performance buildings. So just to show you some basic results, you know, like again, you're starting out in an R4.3 for the spandrel section, you're going to R9.7. So the vacuum insulated panel by itself makes a, you know, very significant difference. Now, if you're clever, you're going to notice that this R9.7 is pretty close to the R value if you put, you know, spray foam and bad insulation. So I wholeheartedly agree with that. But the thing about this is if you put a vacuum insulated panel in between glass, you can still actually also add insulation and spray foam, which helps get you to even higher levels, so potentially an R15 depending on, you know, the combination. So again, depends what you need from your spandrel section, but when you're talking about, if you need to get basically anything above R9, well, what we're doing right now is not really going to get us there. So it really depends on the building and what level of performance you need from your spandrel. What are your other options from an energy performance perspective to achieve your objectives? So from a window wall situation, we've seen a lot of promise in this type of technology as well. You go from an R3 to an R9, which for a window wall system is obviously, you know, a very robust system without, and then, you know, the benefits are that, you know, potentially you don't need to finish the backside or things of that nature, which, you know, again, those potentially have significant implications for, you know, a project in regards to cost trade-offs. So I will not go through in detail in the case study. Basically, what I will do is just highlight to you some key points. So again, when you're looking at technologies, what you want to do is do a cost-benefit analysis. This is a project where, you know, we were involved where it was a rental building, so there was a lot of emphasis on energy. You know, we evaluated the energy performance from an envelope perspective. We were surprised at how badly the building performed. The building overall was an R2.6. Obviously, most of the energy is going out of the vision area for this building. We noticed that changing the glazing ratio had a very large impact on, you know, obviously improving energy because so much energy was going out through the vision area. And so we started looking at tweaking the glazing ratio, which is, you know, the first step to try and improve performance. But obviously, in this project, that wasn't going to get us where we needed to go, so we needed to evaluate other technologies like manufactured structural thermal breaks and other components. Essentially, we did a cost-benefit analysis, which helped us identify the most promising options. So from a payback period, 2 options stood out, which were either a manufactured structural thermal break or a triple glaze system. And essentially, that was the solution that was adopted for that project. So again, it helps you identify some relative options when you start evaluating payback so you can decide where's best to invest that money in regards to improving my envelope. So final comments from a best practice perspective, you know, what I encourage you to do is shift from thinking about nominal R value thinking to whole building R value thinking. So it's not just about, you know, the R value of your spandrel or your vision or your opaque wall. You really need to start looking at the overall facade when you're talking about energy as to how does your overall building perform from an energy perspective, the facade, and what kind of improvements can you make, and where is best to invest that energy. And then look to the building envelope to achieve energy savings, because increasingly as you push higher performance buildings, the envelope is dragging you down and you need to really look at improving its performance. Plan early, so whether that be through design charrette process or through analyzing energy modeling at early as possible and doing lots of different simulations. I found that a really powerful tool so that as a design team we can get together and really decide what are the routes are the best approach in order to meet the targets that we're setting. And last, you need to really be prepared to look at new materials, because in order to reach the high performance targets, you're going to, in the next 5 years, going to need to start incorporating different materials into buildings that you probably haven't worked with before. So if you're looking for this thermal guide, here's the link to that. And that's pretty much it. Thank you so much.